they don't make the micrologics anymore, or even the SLCs. They've moved on to the 5000, but what you learn in this is you'll be able to pick up the other languages really. Applications. So this is not in your book, but I wanted to show y'all this. These are different ways. What they're trying to do with PLCs, of course, when PLCs first came out, basically they were taking relay logic and converting it over to computers. So what they wanted to do was come up with a programming language that people that understood motor controls or these relay logic circuits could program a PLC. So this is where they came up with this ladder logic language. What they did over time is they realized that they had different people coming in through PLCs that had came up through different disciplines besides electrical control, besides remote controls. So they wanted to get people who came up through computers and understood digital, right? They didn't understand ladder logic, but they don't understand digital, ands, ors, and nots, which basically we use a bunch of symbols. They wanted to understand people that understood flow charting, so they came up with a way we can program a PLC where we can use flow charts. They came up through languages where people had been programming in C and Pascal and these other high-level computer languages where they could come in and they could program a PLC without having to learn ladder logic. And then they have a language that's very, very similar to assembly language, which is one step up from machine language. So this is structured text right here. So this is a text-based language. It's a script-based language, and this would be controlling either a PLC. This is actually written for a microcontroller called Arduino, which basically the only language it programs in is structured text. So this language right here would be for people that came up through computers, programming computers, right? But building applications, not running applications, building applications. This is called function block diagram, or FBD. This is digital. So these little symbols up there, those are ands, these are pulses, ands, I don't see any ors, these are ands, these are greater than equals to, this is what we call the SR latch, this is digital, guys. So instead of me trying to learn ladder logic, if I came up and I understood digital, this language right here would be the language I would love. This language is very popular. Most of your languages in Germany are written using sequence of function charts. This is flowchart. So you start off with a statement, and then you start off, okay, I'm going to do this. What's required to move to the next one? And this is sequence of function chart. Germans love it. So, and this is really neat because you can use these to really troubleshoot. They're easy to troubleshoot with. If you take the AUT 208 class, we'll look at these a lot. This is the instruction list. This is basically very similar to assembly, where you assign mnemonics to each instruction, and then you put what else you wanted to do. So this is the instruction text. This would be for people that really in computers for a long time. It's really close to a programming language we call assembly. This is ladder. This is what probably 90% of the PLC is programming in. So it's a high probability, extremely high probability that you know how to do this, right? Make sense?
So why does the Germans like that?
They just like it. I mean, they just like it because of the way it's set up. It's real easy to understand the flow of it. So you're not dealing with rungs and trying to figure out what each rung does. You see the actual flow, what's required to move from this step to that step. And it's usually going to be a sensor. This is the way we'll look at it. This is the one that's made available. Let me see if I can find it.
Aren't most PLCs German or European made?
No, the biggest majority is made right here. Allen Bradley is made here.
I know Allen.
And then following them is probably Siemens would be the second leader manufacturer. But then we got all of these different PLCs out there. microcontrollers, which cost about $30 a pop. Those program in structured text, and those are only $30. You can, in the application is free to program those. So we're going to run into a lot of those, and those only program in structured text. Let me see if I can find a. This is a little simpler, but you should be able to see if this is what I want. If it pops up. So this is where this would be the step up if I get it. Okay, there we go. So this is flow chart. So it says, okay, I start, I have to hit, 4B1 has to be true, and B1 has to be true, and I have to press the start button. So if it's over there on the, somebody, I think, press the start button, that's that green button up there. If all that's true, it'll fall into the first step. This will output Q, this will output Q, which is output 5.4.5, and this would affect system 1B2. If 1B2 is true, then it falls into this next step. If 1B, if this is true, so I'd come up here and I say, okay, I say this guy right here didn't retract. Well, what am I going to look at? I'm going to look at that sensor right there, and I'm not trying to figure out how the ladder diagram works. Well, if I can do this, and I can program it this way, it's a lot easier to program because you're not trying to say, do I want to hook these in AND, do I want to hook these in OR, do I want to do this, I want to do what's required to move from step to step. And this is the power function block.
I think I like that better.
Yeah, see how easy that is? For troubleshooting stuff.
Yeah.
Yeah, so you say, okay, what didn't happen?
Right.
And this is what didn't happen. What step was you in? Well, I was in step 6. I didn't get to step 6. Well, what was needed to get to step 6? Well, this 3B1 sensor had to be true. So you don't have to start from the front and figure out how a ladder diagram works. So these guys, and this is not actually the language, but this is still it. If I could bring it up a lot better. That is it. That's the same way. This is actually what it would actually look at in a PLC, right? That's it. So this would be a step. This would be what's required to move this. So this says reactor empty, right? Then that would fall into this step. Change A, if this is true, it'd fall into that step. So this is actually giving us the names instead of the actual IOs, and that's the power of this language right here. It's really cool. We got to play around with it a little bit when we was over in Germany.
It's got to be simple for most alcoholics. And
yeah.
I work with a lot of Germans and Russians.
We downstairs in the hotel. Downstairs in the hotel, they had a drink machine down there, and there was beer in the drink machine.
Yeah.
So them people drink some beer, and they do have beer. Well, I don't know. They drink a lot of beer. So this is what I'm going to do. So this is the program. So all I'm going to do is I'm going to go ahead and bring up our list. I can not connect to my PLC right now. It don't pick up the driver, and I don't have a right Ethernet cable on there, but I'll show y'all that. So this is RS Logic 500. Come on. Okay. And this is the way it loads. So first of all, we would have to do is we're going to have to say, okay, so I'm going to come up here and I'm going to say new. And then if it catches up with me, guys. Now, first thing in every PLC language, the RS Logic 500 has the ability to program a bunch of different PLCs, a bunch of different CPUs. So the first thing these applications are going to do is they're going to ask you what CPU, what PLC are you going to program? Because once you do that, it knows its inputs, it knows its outputs, right? You understand? It knows the machine language that processor understands. So this would be like me trying to download an application for an Android application onto my iPhone. I can't do that because the processors speak a different binary language. So this would be all the PLC CPUs that this language supports. Here's MicroLogic 1000. So this is the one we have, B series. Now the next thing we would do is if we've got any modules over on the side, then what we would have to do is we'd have to come over here and then we would select what module we're going to attach to the side. So this is the different modules that this PLC supports. We wouldn't have this on this PLC because this is a true fixed PLC. This is a hybrid PLC. So this is all the ones we can support. On this one, we can put four things on the side of this one. That's all. So I'm gonna vary on that. Notice it's only got 4 slots available. Y'all see that? Okay, we're not gonna do it. Then this is a rung. It starts off. RSLogic 500 starts off with the N rung. This is the rung when it hits at loop. You cannot put anything inside this rung. So what I need to do is I need to insert a rung. The most often used instructions are right here. So here's a rung. I can come up here and drag a rung down. See the little thing turn green? That means I can insert. So it's got a rung. It says I have an arrow right off the bat. See the E's over on the left-hand side? Why do I have an arrow? I have no outputs and I have no inputs, right? So what we would do next, we'd say, okay, I want to pull an input down. So this is an input. It could represent anything. I'm actually going to make this represent one of my switches on the front. Okay. And then I'm going to drag a stimulated relay coil, and it goes right there. Okay. Now notice I got a question mark above it because I haven't told it an address, right? So what we'll do is we'll come up here and I'll go ahead and make a fill-in circuit. So I'm going to go ahead and pull some stuff down. Now the down drop, this is the down drop right here. And when I want to pull something in it, I come over here, grab it down at the bottom, and then I can move it. And notice the little thing turns green. See that? And then that's where it's going to pop at. And then we'll put another one right here. Everybody okay? So far so good. Is that hard? So I'm gonna come up here, I'm gonna assign this an address, and this is the scheme. So we come up here, if it's an input, so this means I've got something hooked up to one of my input ports up here. We start off with an I, we put a code, then we put a slot number. On this, the slot is 0. This is built in, so I'll put 0. Okay. And then I'm gonna say I'm gonna use input 0, and that's the address right there. So what I've just done is I've assigned to whatever guy is hooked up to this one right here. Okay. Which of course is switch 0. Okay, when I hit enter, it pops up. Unfortunately, it defaults to comments. I'm not going to use comments right now, so I'm going to come up here and I'm going to call it stop. And then I'm going to hit OK, and it puts the symbol name at the top. But look what happened to the address. It put the slot number, so this is input, slot 0, bit 0. Everybody okay? That makes sense? Yes or no? We okay? Okay. And then what I'm going to do is I'm going to assign this guy. I'm going to call it input colon 0/1. So that'll be the second switch. I'm going to hit enter. And then I'm going to call this guy start. Everybody okay? I'm going to go on this one. I'm going to assign this to that coil. I'm not over there yet, but I'm going to O, stands for output. Okay. And then I'm going to go to slot 0. These are the internal ones. And I'm going to use output 0. Okay. And I'm going to just call it, I'm going to call it M1 for the heck of it. Okay. So I've assigned it a symbol. So now over here, I can just call this M1 and it'll give it the same address. because I already gave it a symbol name, right? Okay. So what we're going to do, we're going to see if it's going to compile okay. So this, on RS Logic 500, this does not clear automatically. We got a little thing up here. Can y'all see the little computer with the check mark on it? What this is going to do, this is going to see if there's any errors, syntax errors in there. I click it, notice my E went away, so that means it's okay. Okay? Makes sense. There's my program. Now, if I was connected to my PLC, then the next thing we would do would be download it. But anyway, I'm not connected. I don't have the Ethernet cable. I don't have the right Ethernet cable. So let's do that. We'll do another rung. So I'm going to come up here, click on that, drag another rung down. Notice the first rung in your diagram is always rung 0. Okay. And then what do we want to do?
Run input.
Yeah, we can come up here, right? You understand? I could come over here. I can put coils in parallel. So I can put a down drop right here. Now the down drop, notice it went here, so I'd have to grab this down at the bottom. I slide it over so it turns green, and I put that right there. And now I can put the other coil into here. So that would be a parallel circuit, right? And then what would I have to do? Well, I'm going to have to assign addresses. This guy right here can have as many, so when I'm dealing with a relay, you're going to be defined by the number of mechanical contacts that relay has. Here, guys, I could have contacts up to 200. I could have one relay with 256 contacts on it. But they're simulated, right? So I'm going to come down on here, and I'm going to assign this contact to that simulated relay. And I'm just going to call it M1. So if I've assigned it a symbol, it goes ahead and fills in the address information for me. So this is assigned to this guy right here. That makes sense? You can't start off with a symbol. I'm sorry, I need to get it different. So you can't start off with a symbol. I can't say M2, right? How did you do that? Oh, I screwed up all this. But I was changing them up there. But we can do this. So let's change this. We can do this. I could come down here on the right. This is called a project tree. This is over on the left-hand side. So right now my controller doesn't have a name. We can name it. This guy, the way RS Logic 500 is set up, it's set up where the memory is defined. So what they do is, this is different file numbers. One of them they call S0 and S1. We can't do anything with those. I don't know why they even do that. This right here is called ladder 2. So this is what I'm programming in right now. Notice down at the bottom it calls it what? File 2. If I want to give it a name, I can come up here and right click on that, and then I can rename it, and I can call it red. And what you notice when I hit enter, the tab change. It's still ladder 2. Technically it's in file number 2, but you can give the tabs any name that you want to give. Okay? Makes sense? This is what's going on with my inputs. So what I'm going to do now is I'm going to go up and bring up, since I can't connect to my PLC, what I'm going to do is I'm going to get out of this. I'm not even going to save it. And I'm going to bring up this simulation program that I have, which runs an interpreter. Oops, it's called Logic Pro. Very, very similar. But what we can do is we can simulate it. This is really cool because you can actually write programs to do things. So I'll show you some of the stuff. This costs about 45 bucks. But you don't actually have inputs and outputs. But if you really wanted to get into this and learn how to do it, you got all these different simulations that you can set up, like a door simulator. I think I've got this written, where they give you the inputs and outputs, and you literally write the program to control this door. But it's simulated, it's not real. what we're going to use is we're going to use the I/O simulator. Which is this guy right here. So I've got a bunch of push buttons over here, and I've got a bunch of lights that I can turn on. So I'm going to do the same program. What do I do? I'm going to click on that. I'm going to drag it down. Same thing. Turns green, right? It's not a green.
What's that symbol called?
What's that?
Wrong. Okay, wrong.
It's called wrong, right? Are we okay? It's not inserting wrong for me.
It's not a cell phone. That's on Blackboard?
No, this is something you buy. I can't give this to you. Cost you about what? $45. I could put the link up there where you could get it. And it's not real. You can't get credit for your labs with this, but you could do them first and see if they work, and then come in, and then it'd be just a process of translating over. But I can't do anything then. Okay, get it there. I don't know what it is. So same thing. I'm gonna do the same thing. This thing doesn't do symbols right, so I'm gonna come up here. I'm just go ahead and pull 3 contacts down, and then a coil. Then I'll do a down drop. And we'll pull this one into here. Try to anyway. Pull this one into here. Okay. Now this is in slot 1, so notice this is input. This is in slot 1 because this is simulating a modular PLC. So in a modular PLC, the first slot you have available to you is slot 1. In a modular PLC, slot 0 is the CPU. Since this guy, the CPU, and this is together, then we just don't have a slot, so we use slot 0 instead, right? Does that make sense? So I'm going to come up here and I'm going to say input colon 1/0. It just don't ask me for symbols. I'm going to call this input colon 1/1. Here I'm going to say output colon 0/0. Oops. I need to put my colon, output colon 0/0. Another thing that RS Logic Logic Pro doesn't do, you don't start off with an error over here. So that means you can do syntax errors, and this guy here won't know. So I could put calls in series. If you try to do that in RS Logic 500, it would say, so this is a simulation, right?
Give it up and take it work.
Oh, I'm sorry. So the first output is slot 4. Yeah, that's not going to take it. Okay. So once I got the program in there, then what I would do is I would come up here and we'll download it into the simulated PLC. We're offline, so no, normally it's over here, but on this one it's actually up here. Okay, so we download it into PLC, and then I'll come up here and I'll put my PLC and run. This was on RS Logic 500. If an input is active, it's going to turn green. On the Logic Pro, it turns yellow. That's what I'm talking about. So notice this is the input. So this would be literally physically wired into input 0. And this is in slot number 1. Notice when I make this contact right here, you see it turning yellow. It means it's true. Okay. So what I'm going to do is I'm going to leave this closed all the time. You can change these into momentary contact symbols. So what are we waiting on? Push button 1, right? And then it should turn on this light right here. So this would actually be thing out there. It turns on that light. Sealed itself in, right? Y'all see that? So the light's on all the time. You don't see it? What's it waiting on? How do I stop it? Huh? How do I stop it? How do I stop it?
Click the output.
Well, look, this is a normally closed push button. So when I start it up, it says it.
Convert the circuit then.
So I just press the stop button, right? I guess I should have gave that name, right?
Spring,
Huh?
spring, Rick.
So notice, this is a normally, you say, well, that's a normally open it's not. I got it hooked up to a normally closed switch, so it's true all the time, right? Y'all see that? So see it's yellow, it's true all the time, because I got it hooked to what? A normally closed switch. And this really gets people that motor controls messed up. And what are we waiting on? It's waiting on me to press this little switch right here. Right? As soon as I press it, then it's going to energize this coil. But that coil is controlling this output right here. Now what could be connected to this output, wired to this output? We got a light wired out there, but what could it be? It'd be a real small motor. PLCs cannot run big loads. It can run coil. Yeah. So I could run that big relay over there, right? You see that. It could bring in that coil and that relay down at the bottom, and then I could turn on that motor down there with it. The PLC can't do it.
The indicate light.
Right. So what are you saying?
Indicate light, like a green light.
Well, that's up to you. All I'm saying is I don't have to wire a light to this output. I could wire anything to an output, right? A load. I don't have to put a light. You could put a solenoid out there. You could put a small motor. You could put a relay.
You
right?
probably run what, a small.
Very small. We're talking about
power.
fraction, huh?
Yeah.
No, not
You
even.
run one?
No, not even close. You couldn't even run that. That's a half horsepower over that. But that's AC anyway. Here, the output might be DC. This output is AC. 120 volts AC, so I could pick up that coil right there with this thing, and then that could run the motor. Right? You understand that? You don't have to run a light. Here it does lights, because that's what you're going to do. You're not going to turn on motors. You're going to turn on lights that says it's going to be a motor, right? You understand what we're saying? So I got a box I'll hook up to this once I get it connected. I have to find the driver for this dongle for this USB RS-232. RS-32. I think I might have it. Nope, I think I got it down in there also. So here's the project tree, right? You understand? Everybody okay? They don't show you ladder 2, so it's not the same. So what we got is in fact, I might go down there when no, dang it. I didn't bring this computer don't have a DVD on it, and I didn't bring my DVD, so I couldn't install the driver anyway. I know what I can do. I'll take a 10-minute break. It's becoming one of the most popular ways of connecting a PLC because it's readily available and there's all kind of support out there for it already. First thing we have to do on this guy is we have to run a program called RS-Link. And what's the driver? What's the driver in computers? Huh? What's that? I hope not. So everything, I'm sorry, I didn't mean that. Everything inside the computer is run by a program, period.
Drivers run
No, drivers run hardware. A driver is a machine language program written to drive a specific piece of hardware.
That's why you only have it for your graphics card, motherboard.
Right. Well, the chipset on the motherboard. Yeah, chipset on your motherboard. So, and a lot of times you will install and you put a USB device in there, so I got to install the driver. So what the operating system is, guys, is just thousands of drivers, but it still can't support everything. So it means if it doesn't think it's going to support it, they're not going to put it in there. So you're going to have to install the driver to make it work, right? You understand that? Add that to your operating system. And then the operating system is tied together by one program called a shell, and that's what Explorer is. That's what you're looking at, and that lets you control the operating system. So applications do not have drivers, and they're called applications because they apply the drivers in the operating system to do a task, right? You understand? That's why they got the name applications. Okay, so if I'm going to hook up this PLC, I've got to tell RS Logic to install the driver. So this is called RS Links, and this is where we install drivers. This is the way we communicate with the PLC. So right here, I'm going to go to communication, and I'm going to go configure drivers. And this is the list of all the drivers. This is the number of ports this guy supports, a lot of. Originally, I was using RS-232 DFI, but the problem is I didn't have the driver for the little dongle that converts it between USB and where's it at? Yeah, so I unplugged it. So this is the dongle right here. This is the guy that converts it from RS-232 to USB. And I don't have the driver for this. I got the driver now, but I gotta have a DVD drive to install it. So I installed an Ethernet device. That's what I'm doing. Then I add the driver, and that's what popped down there. Now it's running. Okay, that makes sense. Then what I have to do is I have to assign an IP address to my PLC. So I got to use another application called DHCP, which is a Dynamic Host Configuration Protocol, which is a software package that automatically assigns IP. Okay, so I'm going to connect this to my Ethernet card, which is this guy right here. And then what it's going to do is it's looking for a MAC address. MAC addresses, did we talk about that?
No.
A MAC address stands for Media Access Control. This is the physical address that's built in anything that's going to connect to an Ethernet network. Whether it's Wi-Fi or anything, everything's got to have this physical address called a MAC. Most of the time, I know on my iPhone, which is out my car, I could bring up the settings on the thing, information, and it shows me the MAC address. So everything's got to have a MAC address. It's 48 bits, but it's not going to do it in binary. What base is it using? So this is a typical MAC address. 3C97, it's 48 bits. The first of the leading, so the 3C970E, that's what they call a manufacturer's ID. So everybody can't do this. They've got to be assigned this by, gosh, I can forget who manages MAC addresses. And then the last digits would be, the last three would be the actual digits assigned to a device. So if I was going to make a device that needed to connect to an Ethernet network, I would have to contact an authority that handles MAC addresses, and then they would give me a manufacturer's address. That's 24 bits, so I could have 2 to the 24th different devices, and if I run out of that, I can get another manufacturer's address. I'm waiting for the MAC address for my PLC to pop up. It might take a little while, but it's 03. The manufacturer is on this one is 0F. I could bring it up on a manual. Most of your PLCs will put the MAC address on the side somewhere if it uses Ethernet IP. This guy don't do it. You have to go into a manual and look at it. If it don't pop up, guys, I'm gonna have to. So we're looking for 000F to pop up there. Come on, come on, come on, come on. Oh, no. It's got one. Hold on. It's not gonna pop up. I had it. Now what we have to do is we have to put it in the same subnet that my computer's in, and I'll show y'all this pop up in a minute. Let me make sure it dropped out. Yeah, it's going. So this is probably the MAC address for my one of my network cards. So if the device don't have a MAC, it don't have an IP address, it comes up and looks for what we call a DHCP server, which is Dynamic Host Configuration Protocol. And then this will assign it an IP address. But I'm on it. So this happens automatically for you. This one says we're not connected to a network, a DHCP server, then I've got to run. If this don't work, then we're not going to be able to connect to this thing. It finds that guy right off the bat. Doesn't it? This computer, I'm resetting it up. This is not my normal computer. So. We're looking for 000F7 something. With AC modules, we don't have to worry about anything because AC has no polarity. But when we deal with DC modules, DC has a polarity. Everybody understand that? So the way we're going to do this is we're going to come up here and we're going to have a power rail for my inputs. This is not L1 and L2, guys. This is my power rail for my inputs. And this is my power rail for my outputs. Now, common, most people think of common being minus, but that's not exactly true.
That's a ground?
This is just, no, it's just two power rails. I don't have to have ground, right? You understand? I can wire things up and they work without a ground. Does your cell phone have a ground? No, okay. But it's got power in there. Now, so it's got two lines. It's got a plus and a minus. It's DC. You know, but what we're dealing with is we're dealing with this rail right here. We'll say I'm gonna hook up my inputs on this side. So let's say this is input :0/0. And then over here, I'm gonna hook up my outputs. Let's do it. Let's actually simulate a drawing. So let's say I come over here and, okay. Now, if I come over here and I make this a plus, and what's my input port looking like? It's an input. It's a load, right? What do we need? If I got a plus over there, what do we need to complete a circuit? Yeah, so that's what I'm saying. If I came over right here and put a light bulb, it's not going to work. So if I call this plus, what is it looking for? It's looking for a minus, right? You understand that? Okay. So that means if I come over here on my input port and I reference all my inputs, so let's come up here and redo this. Because this is an important concept. So let's say I'm going to use a push button for an input. A push button. And it's going to come over here and it's going to hook up to an input port. Now, if I come over here and I hook up my push buttons to plus, so let's put up another push button down here. And this is another input. Let's call this 0 and 1. What's got to be on this side over here on my PLC to get current flow? I got a plus over there. What's required over here? A minus. So this has to be a minus. Okay. Now, what this does in PLCs, this came up through digital. Anything that uses a plus as a common, we call this sourcing. And anything that uses a minus as a common, we call this syncing. This only applies to DC.
Yeah.
So that means if I come over here and this common over here is minus, and it's common, it's not, common is just where things connect to. So all your push buttons are going to connect to a common. Is it minus or is it plus? It could be either one.
Minus column.
Syncing. And this came up through digital, guys. This is DC. AC has no polarity. So if I had inputs, we would have a common. We wouldn't have, yeah, but it's, you know, okay. So what happens is, then if I came up here, I keep hooking up input devices. Then over here on my PLC, I'm going to use a negative common. So if I'm going to use sourcing devices like a sensor, a sourcing sensor, then it's going to have to have a plus common, and then my PLC is going to have to run a minus common, right? Makes sense. So if I'm using syncing input devices, my PLC inputs, if I'm using sourcing input devices, my PLC input has to be syncing. If I'm using syncing input devices, my PLC input ports has to be sourcing.
It can alternate.
So when I come up here and look at this input port right here, oh, hopefully it's like that. I might have to turn that. Let me see if my camera's still going. I think it is. Yeah, it's hooking up at the ceiling. I'll see what this.
See a little bit.
This says at the bottom. This says these inputs are syncing. So all the devices I hook up here has to have a positive. It's going to be positive. The output devices is sourcing. So that means here,
The negative.
my devices that I hook up to the output is going to have to be hooked up to the negative, right? Does that make sense? Now this only comes into play for PLCs. So what we can do with this PLC, this is pretty neat, is that notice up here on DC, if I can get it up here. My camera up here. This is not good. Can y'all see this? It's got a common right here, a DC common, and it's got a DC common. What can I hook up there if it says common? I could hook a plus or a minus. So, but we can't set the common on every one of them. This one sets the common on this group, and this one sets the common on that group. So I can set up these 4 for syncing, but I can set up those 4 for sourcing, whatever I want to. But your devices have got to be opposite, right? You understand? Yes or no? Now down here, so up here I've got the negative running up here. I don't know if you can see it. Down here I've got the positive. Now here what we have on this one, since this says relay outputs, I have a common for every output. But it says I could put DC or AC. So this is the advantage of a relay output has, is a relay output, don't care if you put AC on there, if you don't care if you put DC. Well, what I have is I have the positive coming over here. So I've wired this PLC up for syncing inputs, sourcing outputs. So if I got syncing inputs, then my devices are going to have to be sourcing, right? You understand? Over here, since I'm using a sourcing output, then my output devices have got to sync. Y'all understand this? Over in the U.S., this is the predominant way that we hook up these DC PLCs. Is we hook up the inputs as sourcing and the outputs as syncing. I'm sorry, the actual input as the input would be. So this is the way our PLC is hooked up. This is hook up the source, so this is going to hook up the load. Now, in sensors, we have 2 types of sensors that I'm not going to explain, but an NPN sensor, this is a syncing sensor. And a PNP sensor, this is sourcing. That means if my PLC is hooked up like this and I buy a syncing sensor and hook it up to a syncing input, it's not going to work, right? You understand that? So if I've got a syncing input, then all my sensors are going to have to be sourcing, and this is just something you have to know about. I'm not going to explain it to you unless you take solid state, and we'll talk about NP and PNP transistors. But this is the way you buy these things. So PNP are sourcing, right? You understand? NPN is what? Syncing. So some PLCs give you the ability to configure it, whether it's for syncing and sourcing. Some PLCs, that's fixed. Allen Bradley has a tendency on their PLCs to let you decide, unless you get a modular PLC. So modular PLC, you're either going to buy syncing inputs, right? So this guy's got syncing inputs, and it's got sourcing output modules. But you could buy a module that's opposite, right? You understand? So it all depends basically on where you work and what they come up and they decide to use. So this is what we got to do. So this is what we have to do. So first of all, we have to establish a common. Now this is done for you in the modular PLC. So the output on the modular PLCs is DC. That's what it's going to be, right? You understand that? On these PLCs, you're going to have to establish a common. Okay, you understand that? So if you can see this, what I've done is, first of all, I need to bring up that blank. So this would be either an external power supply. So most of your PLCs have internal power supplies, but they're not intended to run a big load. So just about all the PLCs in the industry is going to run an external power supply. Because if you use a solid state sensor, which is very popular, these are electronic circuits and you have to power those up. And your PLC power supply cannot power 100 sensors, right? You understand that? So notice what I have here. So here's my power supply. I've got the negative pointing toward the common on my input ports. So I'm setting up my inputs to what? Sync. So my positive comes over here to my input devices themselves. And notice this is its common. So these guys, since I've got the plus running over here, these guys are set up to source, right? Don't understand that? That makes sense. Now on this one over here, I've got the positive coming into the common on my PLC. I've got it wired. So that means the actual output ports are set up to do what? source. So I'm gonna come over here on this one. All my output devices are gonna connect to this common right here. This is minus, so these output devices have to be designed to sync, right? That makes sense? So this is pretty important. This guy here has AC outputs. So here I would use the symbol for an AC, and so if you got the one of the 1000s, this is the way you'll wire your connection. So we're using sourcing inputs, syncing inputs, so sourcing devices, and then over here don't make any difference, right? You understand that? So remember, this common right here is 120 volts, guys, on the 1000s. So don't open the little door down here at the bottom. Are we okay? Any questions? So this is the way the program runs. So what we do is basically between your inputs, so we input from some type of input device. Then we're going to run this input through our program. This is not wired, guys. This is the flow chart. Then eventually we're going to output. We're going to generate a what? Output. So the sequence it goes, it starts off with a rung, and it works from left to right. So the first thing it's going to do is it's going to scan the inputs. Once it scans the inputs, it's not going to go. It's going to run through the program, decide what you want to do with the inputs, and then it's going to eventually generate an output. Does that make sense? So that's a scan. The scan used to be long. Now the processors are so fast, this is almost instantaneous. Once it does one rung, what would it do next? Fall down to the next rung, the next rung, the next rung, right? That makes sense. And we call that a scan. A scan cycle would be how long it takes to scan your whole ladder diagram. Does that make sense? So the longer these programs are, in the old days, we had problems because the CPUs wasn't as fast. And when our ladder diagram got too long, it would literally miss the inputs. From top rung to bottom rung, moving through the entire PLC ladder diagram. So two things: scans inputs, runs the program, or takes it through your logic, then eventually generates an output. And it might not be an output port. We'll have to look at that too. Are we okay? We okay? And we can look at the scan time. RS Logic, the Logic Pro kind of simulates this. But I'll have to show y'all where you can actually look at the scan time. And once you get into the instruction set for the processor, every instruction usually, y'all know what an instruction is, right? What would you think a computer instruction is? Yeah, well, it's one thing though. It's one thing that you're telling it. So when I come up here and draw this logic diagram, that is an instruction right there. That's one individual instruction right there. Okay. Okay. So that would be 1, 2, 3. This rung would consist of would consist of 4 different instructions. Now, of course, we're using symbols, right? You understand, which makes it easy. I can show y'all in the 1100 where it shows you the time it takes the processor to execute every one of these instructions. So you can calculate your scan time. And there's some tricks that we could do to compensate it. Are we okay?
Yeah.
And then once it gets through with this rung, what would it do? It drop down to the next rung. And then it goes next rung, next rung. Then it hits this N. What does the N tell it to do? It tells it to go back to rung 0.
So go top to bottom.
Top to bottom, left to right. Top to bottom, left to right. That's the game.
Okay.
And it's just constantly looping, constantly looping. That's all this program does is looping, looping. As soon as I switch this thing to run right now, that's what it's doing. It's just sitting here doing what? Looping, 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 looping. And that's what this end instruction. We can't put anything in there. This instruction, we can't put anything in that rung right there.
So that last line will always just be
End.
blank.
It automatically comes in. So when you create a new program, the end will come in there right off the bat.
Okay.
That's the first rung you'll get. Okay? Everybody okay? Scans from the instruction in the upper left-hand corner, ends with the instruction on the lower right-hand corner. After the last instruction, the lower, what does the scan just do? What? It just loops. And that's what most computer programs do. This program that I'm running right now is just sitting there looping. Sitting there looping. Right? So that's just about what all programs do. If it did it, it would flash this up on the screen one time and it would be gone and you wouldn't see it anymore. These are some of our instructions. The output energize. So this is the instruction for us. It looks like this on RSLogic 500 and also 5000 too. This is called an output energize instruction. We'll be using these a lot. The output latch instruction. So it'd probably be better if I bring these up. Let me find our. So here's. Okay, so let's take it back into program. So we'll insert another rung. Okay. And we got this guy right here. This is an output instruction. This is called a latch. Okay. And I'll show you how this works. I'm gonna bring a contact down. Now, if I didn't do that on RSLogic, so let's use another push button. We'll use 0 again. Okay, and then over here I'm going to assign this an output. Yeah. What do you mean the parentheses? No, it does it automatically for you. That's just the symbol. See the symbol? We don't need the parentheses. That's the symbol I'm trying to draw.
Okay, all right, good.
So this is, when I drag this down, that's the symbol that's going to put in there. So you don't have to draw the symbols like that. Because if you had to memorize all those symbols, 0, so we'll use this 4:1. Okay. Now, this is where we can duplicate addresses. What I'm going to do is I'm going to come down here on the end and I'm going to insert another row. Right? And then I'm going to come up here and I'm going to use another switch. And I'll call this input colon 0 / oh, I'm sorry, 1, wrong PLC. So then I'm going to come up here and I'm going to do the unlatch. And I'm going to give it the same address as the one up above. So this is what we call a latch and relay. So technically it's one relay. So we're not duplicating addresses because it's technically one relay. 4:1. And this, see, that one, it wouldn't have let me by with that. So this is a latching relay. We put these on critical things that we want to stay active even though things happen. Unfortunately, this is that latch. So it's got 2 poles on it. Got one down at the bottom and one on the top. That's how things last. And how long will it stay latched?
Until you release it.
I got 2 poles. I got one called latch. I got one called unlatch. Once I latch it, how long will it stay latched?
Till you press unlatch.
Till we unlatch it, right? So we use these, well, out of US Steel, we have them on our electromagnets, on our cranes, because if the crane lost its reset, these are radio control cranes. And every once in a while, they had battery boxes on them, and every once in a while they wouldn't change the batteries out, and the batteries would go dead, and the crane would lose its reset. Well, when that happens, all the other relays would drop out. But you've got a crane carrying, a couple 1,000 pounds worth of stuff on its magnet. You don't want the magnet to do what? Turn off. So we use latching relays on that situation. So you can see how latching and unlatching relay work. I'm going to come up here. I'm going to download this. At least I can do here. So I'm going to download it. And then I'm going to switch back to run. And let's change this to a normally open, please. Okay. So notice when I come up here, so this is basically, even though it's got the same address, it's still the same relay because it's a latch. So On this guy, guys, you'll always use these in pairs, right? You understand? So once you latch, you do what sooner or later? Unlatch. So watch this. I'm gonna close 0, and notice it turned that output turned on. How long is it gonna stay on? Until we unlatch it, right? So I'm gonna pulse this. I'm gonna make this circuit true. So this is simulating that relay that I'm passing around right now. And it basically is a lot simpler to use than this guy right here. So if I was to show you some of the diagrams for the Festo line over there, man, they use latch and unlatch all the time. No. Sorry. So y'all not gonna write programs like this. Let's see what they do. Latch, unlatch, latch. So what they're doing is they're setting up a sequence. Latch, unlatch. So as it goes through the sequence, they'll unlatch the previous one and latch the second one. So you see this is used a lot. So you'll use these in pairs, right? You understand that? So if you use a latch, you're going to use an unlatch, but you'll give it the same address. Everybody okay? See how that works? So I latched it. Then I can do what now?
Clicking
and unlatch it. And you can see this LED staying on. I mean, on and off. Okay. So then we have a one shot. We're not going to get into that. One shot we'll talk about when we get into advanced programming. One shot basically does exactly what it says it does. Once the input goes true, its output goes true for one scan cycle. Okay, so this is a scan. Are we okay? So it does what? Starts at the first rung. What's the first thing it does? Reads the inputs, runs the program, updates outputs, right? Okay. Then it drops down to the what? And then it just does what? And when it hits this last rung, what does it do? Yeah, it just loops back. So here's the project tree area. So the first thing we have up here in our project tree is we have what we call a program file. So let me bring up this guy, because that one's not quite right. So I'm going to create a new program. What's the first thing I need to do once I create? What's it going to ask me to do? No, I'm starting from scratch. I'm going to hit new. What's the first thing it's going to ask me to do? Check, well, the actual CPU, right? So if you're on one of the 1000s, if you want on one of the 1100s, then ours is the 1100B. If you're on the 1000s, oops, which is back up here. Nope, not just down this way.
Is it older?
This is the 1000 right here. This is the 1000 that we have right here. Okay, that would be this guy right here.
Okay.
Are we okay? I'm gonna go up to the 1100 because it's got more stuff up there. Okay, so this is the project tree over here. Everybody okay? Right. So these are our processors. We'll look at some of these. Next, if I had modules on the side, I would click on IO configuration and I would select what module I've got attached to there, right? You understand that? We're not gonna have to do that. We would have to do it on this one. So if we're on this one, the first thing we have to do is tell it what size rack we have. This is a 7-slot rack. And then we would go in and look at the number on all the modules, and then we'd add those modules. This is the actual system programs. So this would be the firmware. We can't change these guys right here. We can't do anything with them. This is ladder 2. That's the one we're looking at right now. They call it ladder 2. Are we okay? These are our data files down here. So this is my output status. So I can actually come up here, and now this is the actual data file for the output. So if I have an output that's turned on, then this right here would be a 1. If I don't have an output, it's going to be a 0. Everybody okay? This is my input status. So this right here, if it's got a 1, it means that input is true. If it's got a 0, it means the input is false, right? Everybody okay? This is the actual status register. This is where I can go and I can look at the scan time. I can look at a lot of stuff. We're not going to get into this much. But if I was going to have a problem, if an error popped up, this is where I would go and look, and it would tell me what the error was. So right now, this guy should be all zeros. If I've got an error, I could come in here and it would say, it would have a 1 in there that would tell me where the error is at. Are we okay? Yes or no?
Yeah.
So what time is that? Do we have access to that?
Yes, you will.
We will. I can't go on all night.
Do you have the $18,000 application on your computer? Now we get it for I think $275 because we're an educational institution. If you work at a company, now if you went and if you decided to go buy RS Logic Pro, this would be this guy right here. The project tree is not quite the same, but it's the same right here. So what I'm saying is I could come over and click that right there. And another thing that we have the ability to do is and this is why it's important, is right now it's set up to display my inputs as what? Binary, but we could display it in what? Octal, we could display it in decimal, which wouldn't make any sense at all, or we could display it in hexadecimal. So right now we got binary. So what's that saying? If I come over here and hit this key, no, this is not gonna work. Oh, I got it in right. Yeah, I see it's not working. Let me try this guy right here. No, it's telling me this output right here is true. So this is not working. So what would happen is this is not coming up right. Remember, this is a simulation. But if I was to come over and close this push button right there, then the bit that's associated with that would do what? It would go to a 1. This is bit files. We'll be using these. Bit files are really neat. We can use these for a lot of different things. They're used a lot for our advanced instructions. But what we're going to do is we're going to use them for what we call internal coils. These are coils that does not have to use an output. Their contacts do not go to the outside world. So I'm not going to use these things to turn on a light. People don't understand that, and they think if they've got an output, they've got to assign it to an output, right? You understand? But if what that relay controls is don't require to turn on something, then we can use what we call an internal coil. But we use these for a lot of things. Shift instructions, we use them for a lot. This is timers, so we'll get into this. This shows our timers. And what are we going to use timers for? Yeah, just to time things, right? Y'all want to have cars have got all kind of timers on them now. So right now, if you've got a car, you've got an electric fan on there. A lot of times when you turn your car off, the fan keeps running out there. It's on a timer, right? When I unlock my doors, my headlights come on, and they stay on for a certain amount of time. After a certain amount of time, they do what? They go off. When I get out of my car, I open my door, and I close the door, my dome lights stay on for a certain amount of time. So we run into timers all the time. My refrigerator, your washing machine's got timers all over it, right? Your microwave's got timers. So if you've got that many timers, it's a big demand for timers, right? And then counters. And this is as far as we'll get, guys. But we will talk about integers. What's an integer?
It's a number.
It's a number without a fraction,
Yeah.
right? And then the floating point numbers, these are your real numbers. But floating point numbers is where the decimal point can move within the number, right? But these are your real numbers. And real numbers, what's the difference between an integer and a real number? What doesn't an integer have?
Negative.
What doesn't an integer have? It doesn't have a fraction. What does a floating point number have? What does a real number have? It's a number that has a fraction. I tried it. Like pulling teeth, right? So a real number is a real number. It's a number that can contain a fraction. But here, floating point, these can also use scientific notation. And then reserved, and we can actually add more than these. And we're limited on these. This is a big difference between your neural PLCs, is they don't define the data areas. They don't define data files. So what you do when you get into new PLCs, you manage the memory on the PLCs. RS Logic 500 manages the memory on these PLCs. You can make another data file. So I could come up here and, if they'll let me do it. Oh no, this is Logic Pro. No, yeah, this is Logic Pro. If I was over here on this guy.
And it's gonna be on the test one.
It's in the book. So we're gonna go through chapter 6. So this is the project tree. Everybody okay that? Everybody okay here? Right. The two system files, these you can't do anything with those. And like it surprised me that they even display them. Then the ladder 2 holds your main program. Everybody okay? Now you can rename it, but it's still called ladder 2 in the project tree. What's going to change is down there on your tab. In PLC 2, we'll teach what we call subroutines. Most big PLC programs, they take the program and divide it down into modules, and each module is called a subroutine. They'll be in, your subroutines will be in ladder 3 on out. Okay. We're not going to deal with subroutines this term. All we're going to deal is with ladder 1. And like I said, the only instructions we're going to use is the output energize. We're going to use the output latch, right? Unlatch. And we are going to use the bid instruction, which we'll get into later on. And then we're going to use the examine if open and examine if closed. We're really going to have to get into those and let you understand them. Subroutines may be several in addition to the main program. These will be in ladder 2. So, well, let me bring up that other program real quick. Do I still have it? Do I still have it? Yeah, this is the first thing right here. So you can see the way this thing runs. What does it do? So this is the way most big PLC programs are written. They divide the program into modules. Each module does something. So here this program right here is probably around 80 rungs, and I've got problems with something, and I'm trying to find out which rung that's within. Well, what we can do with subroutines is we can take a module and put it out and say this module extends and retracts this certain cylinder. So instead, if I'm having problems with that cylinder extending and retracting, I don't have to find it within this main program. I can find it in what? In a subroutine. Yeah. So you can see right off the bat, this is the one that's running the Festo line over there. You can see this is the main loop. Jump subroutine, jump subroutine, jump subroutine, jump subroutine, jump subroutine. I'm sorry, then we're out of it. But there's going to be some more down here. That's the one shot, which we're not going to jump subroutine. So that's basically the way most programs are written. We'll start off with a main program, and then we'll divide it out into subroutines. And what it does, it makes it easier to troubleshoot. I mean, you can get into some of these ladder logic. I'd hate to imagine some of the ladder logic that's running some of those programs up there. And then you got one programmer that writes it in what we call a straight line program. You know, it's got 100 rungs, and then you got another program another guy that does what splits it up into modules. Which one would be easier to troubleshoot? The modules. Because now you're dealing with something smaller, and you put one task within that module, right? You understand? And now it's going to be real easy to troubleshoot. So we can have anything above ladder 3, anything above ladder 2 will be a subroutine. But if you make a subroutine, if you just stick it out there, it's not going to mean anything unless you put a jump to subroutine instruction in your main loop, right? You understand that? Which is pretty neat. So we're not going to get to subroutines this semester, this term, but if you take the advanced PLC class, that's what we'll do. We're going to deal with subroutines. So here's this guy. So we have a data file for inputs. We have a data file for outputs. We have a data file for status, which we'll talk about it when we get into timers and counters, because you can have problems with those guys. We have a data file for timers. We have a data file for counters. We have a control, which is R6, which we're not going to use this term, but we will get into that in PLC2. Then, of course, we know what the integer is. This is the data file we use only for integer numbers. Integer numbers are signed numbers, but they don't have a fraction, right? You understand that? We'll have to talk about that too. And then we have the floating point numbers. These are going to be real numbers. In fact, Siemens calls them real numbers. And then we have this amazing bit file, which is B3.
So they're the same? Bit 3?
These are bit, yeah, but they're going to be B3 or B10. I think on the 1000 they give you B3 and B10. Well, with the 1100 guys, you can duplicate as many as you want to. So if I come up here, if I'm on this guy right here, I can come over in the project tree, and it says new, and it says, okay, what type do you want to do? Well, I want to make another timer file, right? Now notice we're already using 0 through 8, so it's going to automatically assign it to 9. But you don't have to. You can assign anything above that if you want to. And then I come over here and say okay, right? And I can say timer file 2. And now I say okay, then I got another group of data. I got another group of data. Now what they do is we're limited to addresses of 8 bits. 8 bits, we can have 256 combinations. So that means each one of these data files can only hold 256 different things. So that means I can only have 256 counters. I can only have 256 integers, right? You understand that? But if I need more, I can create, on this PLC, I can create another data file. I can create another integer file. But each one of them, once I create them, then you can put 256 things in there. So inside this counter 5, and inside this 5 right here, C5 data file, how many counters can I have in there? 256, 0 through 255. If I need more, then I can create another counter file, right? It won't be C5, it'll be something else, right? So this is actually T9, but it's still T9 for timers. And then I gave it another name. You need to give it a name down here. These are automatic. This down here is not. If I want to get rid of it, I can just right click on this guy and do that. Delete. Everybody okay? So here's all the data files. This is my output status file. So this is going to show me the condition of my what? Or my outputs. And notice they're set up in words. Can y'all see that? What's a word? 16 bits, right? So we have bits. We have nibbles. What's a nibble?
Nibble is like 4.
Nibble's 4.
4.
Byte is what y'all deal with all the time. What's a byte? 8.
8.
Then we have a word. 16. Then we have a long word or double word, 32. Then we have a double long word or quad word, 64. Yeah, my computers call them quad words. PLCs call them double long words and double long words. These will come into play when we get into these guys down in here, because these are going to be designated a certain bit, certain number of bits, right? You understand within that. This is where I can monitor my inputs. This is where I can monitor my status. And we'll look at this a little bit. This is my bit files. We use these for a lot of things. Shifting some of the instructions that if you take advanced PLCs, we'll get into using the bit files. We're going to use it some this semester. We're going to use it for what we call internal coil. What's an internal coil? Don't need an output. A lot of people don't understand. They'll sacrifice their output and don't even use it. So we'll use that this semester. Timers. We'll talk about these different things up here. What each one of these are. Counters. We'll talk about each one of these, what they are. Control. We won't be dealing with this semester, but we will be dealing it with it next semester. These whole things that we call flags, which gives us indication. It gives us a one indication if something is good or something is bad. This is our integers, and this is our floating point numbers, and that's our data files. We'll look at this. This gives us the ability to force outputs, so I can literally make an output true or false without running it through a program. Guys, you got to be real careful with this. This gets people killed. So as soon as you force an output, you're taking away the control of all the safety that you got built into all that relay logic. But we use this for troubleshooting, right? You understand? We use this one a lot. This allows me to simulate. We call it forcing, but it's actually simulating. This allows me to simulate inputs. So what you can do with this is you got your ladder logic. You can actually simulate the inputs without even have sensors or anything hooked up to the PLC. So we do this a lot while the program is in development. Does that make sense? This is pretty important. This is your address symbols. So this is where you could actually go and assign symbols before you started your program. So I could come here and I can add a new record. I could say input colon 0/5. Right, I hit, I'm sorry. Input, where did it go? Oh, right here. And then I can assign it a symbol. I could call it now. And what we've done here is we've assigned symbols before we even started. Now once I do that, now I can come up here and bring this down, and I can just come up here and I can type it down. And it automatically sticks the address in there for me. A lot of programmers will do this before they even start. They'll do what? They'll assign the symbols, because it's a lot easier to deal with symbols than it is to deal with what? Addresses, yeah. So let's see what else we got. So we've added some more. They leave out a bunch. So this is probably the last thing we'll look at, guys. These are two instructions. One of them's called examine if closed, and one of them's called examine if open. This gives more people a problem than anything that we're going to take. One of the things we're going to take. So this right here is an examine if open instruction. Sorry. This is an examine if open instruction. This is an examine if closed instruction.
Contact.
Those are contacts. So they would have wires coming inside. And when we're dealing with relays or internal coils, this makes any difference, but it really makes a difference in what we do. So that means if this one is, if I've got this hooked up to a push button, right now this guy here would be false. This guy right here would be true. For this contact right there. No, this says it's examined. This says it's true if it's open. This says it's true when it's closed. Well, right now this is not closed, right? You understand? So it says right now this push button right here, if I had these assigned to the same addresses, this instruction would be what? False, because it says it's true if it's closed. They call it examine if closed, but it says it's true if it's closed. This says it's true if it's what? Open. So right now, this guy right here would be what? This guy right now, it says it's true if it's closed. Is this push button closed? Okay. It's open. So this says it's true if it's closed. So right now, this guy right here would be what? False. This says it's true if it's open. Is it open? So that instruction right there would be considered true. If I come over here and press this sucker down and hit that right there, this right here is going to go what? This is going to go true. This guy right here is going to go what? False. Now, the problem we have is that if I come over here, a stop button has to be normally closed. Why is that? Well, let's look at our circuit. Let's look at our circuit again, right? Okay, so let's call this CR. This is CR. We'll call this stop. And we'll call it start. Okay, so I come over here, I press this button, it completes the circuit, CR energizes, closing that contact, and this thing seals it. Okay. So PLC, what people's going to do is they'll come over here and they'll do this, because that's saying, okay, that's normally closed. And they'll come over here and do this. And then they'll use a normally open right there and they'll do this. And then they'll sign this a coil. Right? So this is the way they'll draw it. So no, that is not a normally closed. It's an examine if open. Yeah. And this is going to mess you up. So this is the way this would be programmed in a PLC. So this might be input : 0/0. This might be input : 0/1. This right here might be output : 0/0. And this would be output : 0/0. So people, the problem we have in this class is they've had motor controls and they say, well, I got to put a normally closed thing there. And that is not normally closed. That's an examine if open. Okay, you understand? Okay, so right now, if I'm using this guy right here for a stop button, which I have to use, why do I have to use that for a stop button? Well, what we want it to do in a PLC is that we want it to stop if the wire breaks. So what would happen is this right here now would be what? This is an examine if open. Well, by George, it's closed, so right there would be false. Right? You understand? Okay, so that means I can come over and hit this button right here all day long and nothing's going to happen. So the way this would work is some person would have to hold the stop button down all the time and press the start button. Because I'm using an examine if open. That is not a normal. Here, this would be a normally closed. This right here is not a normally closed. It's an examine if open. So it's true if it's open. So if I wanted to use if I wanted to act as a stop button, then what I would have to do is I would have to come over here and use a normally open push button to make this thing work. So now it worked. Now, what's the problem with using a normally open push button as a stop button in a PLC? Well, what happened if the wire breaks?
Never stop it.
You never could stop it, right? You understand? So what gets people confused is when I come over here in my PLC program and I do what? I come over here, this can't be I got to put an examine if closed to make it true. So now the push button is closed. I'm using the examine is closed, so this guy right here is what? True. And then when I press this one, right, you understand that? And this gets people messed up. Because they say I'm using a normally closed push button, so I got to use a normally closed symbol inside my PLC program. That's false. Just about every time you use a normally closed push button, you have to use an examine if closed instruction. And they don't want to see this as an examine if closed. They want to see, they say, well, that's normally open, right? But it's called an examine if closed. So what does examine if closed mean? It means it's true when it's closed, right? You understand? Which is what we want. This is what we want this one to be. So now I can come over and press this button. This guy right here is going to be what? True, because I'm using a what? Normally closed push button. And I'm using a what type of instruction? Examine if closed. I'm using the examine if closed right there too. And this examine if closed and examine if open, this only deals with inputs. This right here is just a contact that's controlled by what? By the output. And the guy right there, this guy right there that's doing these labs, guess what he's going to use for a stop button? He's going to use an examine if open. All right. So that means we'll have to use normally open push buttons as a stop button. Now the problem is if you use this guy right here, the only thing we've got available is normally open push buttons. So we don't have any normally closed push buttons. Yeah, so these are normally open. But what we'll use as a stop button is we'll simulate a normally closed by using one of these. So these guys here stay. We can make these normally closed. We can make these act like normally closed, right? Makes sense? Because these are nothing but normally open. Not time to go there. Let's see if there's anything else. Went over that. Went over the scan. Went over examine if open, examine if closed, right? And I'm sorry guys, in motor controls, we get people that take motor controls, they'll come over here and do that every time.
I thought it was the same, but I see it's the opposite now.
Yeah, and that's what people gets in trouble. Most PLC programmers, and this is the last thing. So this is the makeup of an address. Okay. So we've been using it already. So what do we start off with inputs? We start off with what? I. Now what's nice about this is that data files are understood for your I's. If this was a counter, then I would have to start off with C5. So this is, we're not going to use this until we get into counters. And next comes the what? Slot number. No, this is the instruction. This is not the slots. This is actually the instruction. Okay. So ours, we don't have slots. Ours is going to be fixed, right? So ours are all going to be 0. Everybody okay? Then what's next? This identifies a word. This depends on what type of module you have. We can buy modules up here that's got 16. It's got 16, so we're using 16s. We could buy them with 32s. That would be 2 words. So if we had one of those modules, then we would have to specify the word. If we don't have 30 over 16, then word 0 is understood. You understand this so far? Yes or no? So this only comes into play if you have multiple words. So right now that thing's got a 16. It's in slot 1, so I'd say in, and then I'd say slot 1. Right? You understand? Okay, we don't have to specify the file number because it's understood for inputs and outputs. If this was a counter or an integer file, we'd have to put the file number on there. Then I would come over here, and then I would do what? Well, if I had a 32-bit module, I might have to put a 1 there, right? You understand? But I don't have a 32-bit module. It's only a 16-bit module, so that's understood. Then I'd put slash, and then I would put a bit. So some of these guys like this only come into play. When does this one come into play? Well, we're not going to worry about that for what? Input and outputs. But if I was going to deal with an integer file, what's the integer file? I. Is it 8 or 7?
It's 7.
7.
Usually 7.
Then I would have to put a 7, so I'd put integer. What's the integer? It's not I, okay, guys?
It's N.
It's N, thank you.
It's N.
Yeah. So I'd have to put N, then I'd put 7. Then I would put a what? A colon. And here we don't have a slot, so we'll just have to talk about that when we get there.
Okay.
So what you use, so mainly what we're going to use here is we're going to have to use a what? In, or we're going to use in or what? Out, right? Okay. Then we're going to specify slot numbers. Since both of ours have the CPU and modules built in one, ours are going to be what? 0. Now over there, the CPU occupies a slot. Over here, there's no slots, right? Understand? And then we specify the what? Since we're not dealing with multiple words, then we'll put a slash, and then what we're going to do is this will be the bit number. So that would be a bit within inside a word. The bits start with 0, and they go through how many bits in a word? 16. So the numbers will go from 0 to 15, right? Okay. We've already looked at these. So guys, we've already looked at all those. So the test is going to go through what chapter? 6. What we're going to do when we come in, we'll come in here. We'll just talk a little bit, but we're going to go to lab. I hope y'all got those lab books, right? Okay. Well, the first lab we're going to do the number system, but I'm not going to make it do because y'all got to do the test. What we're going to do is we're going to do the lab where you're going to sit down with your partner. You're going to come up here and you're going to identify what you have. This is not, if you get on one of these are not inputs and outputs. The inputs and outputs are the ones they're talking about on the PLC. So that's what it's going to do. It's going to say how many inputs do you have, how many outputs you have, right? You understand? Then we'll play around with our first program. So I'm going to be busy then because I'm going to be having to help y'all. I'll come over here and go over how you start everything up and create a program then, okay? All right, so, and then we'll have the test at the end of the class. We'll take our test down at 200 also. Huh?
Math?
No math. Like I told y'all, no math. Don't worry about the math. Don't worry about the adding, subtracting. Don't worry about the division, the subtraction. Don't worry about that. Don't worry about that. I would use a calculator. No, I don't need a calculator. Binary math is easy to me.
Binary, but I'm talking about.
So we're going to go math test on the binary?
We're doing the conversion. I told y'all the very first thing is going to be almost like that worksheet that y'all did. It's going to have the blocks. I'm going to give you one, and you're going to do what? Fill in the rest. There will be a review up there, guys. I'll get that up in the morning, okay?
Most of the test going to be on the chart.
Excuse me?
The most of the test.
It's going to be 2 parts. It's going to be just the chart, and then you're going to have then the rest of it's going to be on computer.
Chapters 1 through 6.
Right. But no math.
We're going to have a review test on there or something? study or?
No, you're gonna have a review that says you need to know this.
Okay, good.
What would it be under?
It'll be under test reviews. In fact, I'll do that right now.
Okay. Thank you. It really took a long time to get ours up.
Yeah, I went in there and put it up.
You did?
Yeah, Caprice sent me an email.
I need to send you an email.
Well, you didn't have to send it. If you send it to the instructor, I'm down on every course, so I get every email y'all send.
Yeah, but I sent it to
So you don't have to send it to me. Just use that email instructor, Luke.
Okay.
And then I'll know. You have to understand, this is Mr. Foster's first time to teach this class, but,
Oh, okay.
but it's just like classes he's taught with us before.
Okay. This is first class or this is?
No, he's taught quite a few
Oh,
classes.
okay.
This is the first time he's taught motor control.
Okay, I got you. Let's see. I still pass it though. I just.
And he's dealt with motor controls
Okay.